We have discussed the timestamping protocol in concurrency based concurrency control of database management systems. And before that we have seen that there are two basic issues in concurrency control. One is that of consistency, that is, we must have a correct schedule. In spite of a concurrent schedule, the schedule must be correct. And the second aspect is that of maintaining maximum possible concurrency. That is, the total overhead, the total time to do that must not be so great, and we must try and reduce it as far as possible. So we have seen the locking mechanisms as well as the timestamping mechanisms for maintaining consistency. Now we will address a major issue of concurrency especially related to locking protocols or any other shared protocol itself. It is also equally translatable for the timestamping business. We will discuss it based on the locking mechanism, and that is called the multiple granularity. We will tackle what the issue of multiple granularity. Now a database consists of many things. A database consists of a set of tables which are translated into save files, and each file consists of records. So if you want to lock a record, it's fine, you just lock that record in that file. If you want to lock a file, then how do you lock a file? Do you lock all the records in the file, one after another? Or do we provide a mechanism for locking only files? If we allow a mechanism for locking only the records, then to lock a whole file we will have to lock 10,000 records, which is a wastage of time. If we allow a mechanism to lock only files, then if we want only 3 records, we will have to lock that whole file and nobody will be able to use that file. So you are going to lose out on concurrency. And suppose you want to lock the whole database, then you have to lock all the records in all the files. Or if you allow only locking of the whole database, then nobody else can use that database. So the question is, let us try locking, let us provide both the locks. You can lock the file, or you can lock a record, or you can lock a database. Then suppose I want to lock a record, how will I know somebody has locked the file or not? I have to check somebody has locked the database itself or not. And if I want to lock the full database, I have to first find out and check and find out if somebody has locked any record in the database. If somebody has locked any record in the database, I cannot lock the database. And if somebody has locked the database, I cannot lock any file in the database. And if I want to lock a record, somebody may have locked other files but not my file, so I should be allowed to lock that record. This way I should be able to be providing the system with maximum concurrency and yet see that inconsistent locking is not done, so that because this may lead to deadlocking situation or basically faulty situation. So to tackle that, we have protocols which are related to hierarchically breaking up the database into portions which are lockable. And maintaining track of what you have locked and how much you have locked, so that you can either allow or disallow very quickly. You can allow or disallow very quickly a new lock or an unlocking mechanism. So that is the protocol which we will follow there is called the multiple granularity protocol. It is a variation of the two-phase protocol which takes care of this. Suppose we break up the database into first into regions. That is, these 3 files is one, these 4 files are one, those 4 files are one. Okay. And then each region has got its files and each file has got its records, and you break it up like this. And now you say I can log this, or I can log this, or I can log this, and I can log anybody in shared mode or in exclusive mode. Now suppose I want to log this record in exclusive mode. What do I have to do? I have to check from this to the root if anybody else has logged either this one or this one or this one. If nobody has logged this one or this one or this one, then it's fine, I can easily and quickly lock it, or I can say no, you cannot lock it, but I have to traverse up the string. This is not so much of a problem. Suppose I have to lock this region, then what do I have to do? I have to go and start checking the whole thing to see if anybody has locked it. Because otherwise, if somebody has locked R2 in exclusive mode, I cannot lock this one in exclusive mode or even in shared mode, because shared and exclusive is not compatible. So I must find out a way of doing this quickly. So for that, my simple shared and exclusive locks are not sufficient. Direct locking is not sufficient. If I log this, I must leave some trace along the path that I have locked something below this. See, if I leave a trace here that I have locked something below this, where I don't know, I have locked something below this, I have locked something below this, I have locked something below this. Then when I try to lock here, I will know that I have locked something below this in shared mode, say. So if I have locked something below this in shared mode, here I know, okay, Baba, I can lock this one in shared mode, no problem. But I cannot lock this one in exclusive mode. When I lock this one means I lock this whole thing. When I lock this one, I mean I lock this whole thing. When I lock this, I mean I lock the whole database. So such locks are called intention locks. So by the use of intention locks as well as actual locks, we are able to quickly have a protocol. We are able to have a protocol which can quickly check a two-phase protocol like we had before, which can quickly check. So we will go through the details of this protocol now. What are intention locks? Intention locks, we have got 5 locks. We had our shared lock. If a node, so let us talk in terms of nodes of this graph, which is our hierarchical representation of our database, and let us talk in terms of nodes of this graph. If a node is locked in shared mode, that means that node and the whole subtree, all the nodes in the subtree below it are locked in shared mode. That is, if I lock this in shared mode, this is the leaf, so this is only in shared mode. If I lock this in shared mode, this means that all of them are locked in shared. A node is locked in exclusive mode means that node and all the nodes below it are locked in exclusive mode. IS is intention shared, IX is intention exclusive, and SIX is shared and intention exclusive. So what is IS? IS says that there is some node below this node which is locked in shared mode. So if R1 is locked in IS mode, it means that there is some node in the tree below this which is locked in shared mode. What is intention exclusive? IX is intention exclusive. What is intention exclusive? It means that there is some node in the tree below this node which is locked in exclusive mode. What is SIX? Shared and intention exclusive. It says if a node is locked in SIX mode, then this node is locked in shared mode, and there is some node below it which is locked in exclusive mode by the same transaction. It means that if a transaction locks R1 in SIX mode, then the whole of R1 is locked in shared mode, and maybe somebody below, say R2, is locked in exclusive mode by that same transaction. So if somebody wants to lock in shared mode R4, he is allowed, because shared and shared is fine. So if this is shared, somebody can lock this in shared mode, and somebody can go down and lock this in shared mode, or may lock this in exclusive mode. This is locked in shared mode, somebody may come and just lock this in shared mode. This is locked in shared, this in exclusive in SIX, somebody else may come and lock this in shared mode, but not in exclusive mode obviously. If R2 is in locked in shared mode, if this is in shared mode, region R1, the protocol will be such that this will have to be IS if this becomes shared. This will become IS and this will become IS. If someone wants record 4 to be in exclusive, we will see what is the protocol, what is the compatibility. The protocol will try and ensure that it is done consistently. We will come to this, the details of the protocol. So we have got these 5 types of locks now: S, X, IS, IX and SIX. And now let us see the compatibility. That is what is meant, and then we will see the protocol. This is the compatibility matrix. If someone wants to lock in shared IS mode, what does it mean? That a node below this in the tree will be locked in shared mode, and the node itself is in IS. That is, there is some other node below in IS. So these two, at this point, this compatibility is fine. There is no problem. Similarly, IS with IX. IX means the node is already locked. Some node below is locked in exclusive mode. Here, now I want to lock some node below, maybe some other node, in shared mode. I should allow IS and IX to go. Similarly, IS and S is true, and IS and SIX is also true. But IS and X, that is, if a node and its tree below are locked fully in exclusive mode, I cannot lock it in even in intention shared mode. So this compatibility is false. Similarly, IX to IS is true, IX to IX is true, but IX to shared is false, because if a node is in shared mode, the whole tree is in shared mode. And IX means I want to lock somebody else below in exclusive mode. Why should I allow that? I just should not allow somebody to be locked in exclusive mode when the whole, I know that the whole tree is locked in shared mode. Similarly, this is not allowed, nor is this allowed. Shared with IS is fine, shared with IX obviously is false, shared with shared is true, and shared is not allowed with SIX or X. SIX can only go with IX, because SIX means shared and intention exclusive, and this is IS, intention shared. So what is the situation between SIX and IS? IS, it means that this is an SIX. That means this is shared, the whole thing is shared, somewhere below is exclusive, and I want to lock it in IS. That means I want somewhere to go and share it. If I want to share here, this should be fine. When I try to share here, I will fail because of the incompatibility between shared and exclusive. But if I want to do a shared here by this fellow, I should be allowed. So that is why IS and SIX and IS is true. That is why SIX and IS is true. The rest is obviously false. And once you lock a node and its tree below in exclusive mode, nothing else is obviously allowed. So this is the compatibility function. Now we come to the protocol. That is, we come to the rules of locking. We will have to lock in such a way that when we want to lock a node in exclusive mode, all the nodes in the tree below it, above it, suppose we want to lock in exclusive mode, obviously I have to lock this in intention exclusive, this in intention exclusive, and this in intention exclusive at least, or intention shared, whatever, or any lower category. If I want to lock this in X, I have to lock this one either in IX or SIX. This will be either IX or SIX. This will be either IX or SIX. Similarly, if I want to lock somebody in shared mode, then this one must either be locked in IS or S. Obviously, if this is S, I need not lock it again. Either this will be intention shared or this will be shared, I think this should be only be intention shared or intention exclusive. If this is locked in shared mode, this may be locked in intention shared or this may be locked in intention exclusive. There is no problem. So we will come to the guiding principles of locking. So what are the locking rules in multiple granularity protocol? The first is an obvious rule. You must always follow the lock compatibility function. If the lock compatibility function is violated, locking is not allowed, and immediately the whole suspend and all that. Whenever you cannot lock, that is, you come to lock an item which is already locked, in the sense that the lock compatibility function gives false, you will have to suspend your operation. The root may be locked in any proper mode. What is meant by a proper mode? That is, first you will have to try and lock the root. And obviously, every time the compatibility function must be seen. How will you try and lock the root? If you want to lock something in shared mode, you will have to lock the root in IS. If you want to lock somebody in exclusive mode, you will lock the root in. So appropriately, the intention lock has to be provided in proper intention actually. If you want to lock it fully exclusive or shared, it's fine. The third is TI may lock node Q in shared or intention shared only if the parent of Q is locked by the same transaction in intention exclusive or intention shared. That is, I may lock a node in shared or intention shared provided that the parent is either intention shared or the parent is intention exclusive. Intention exclusive means below somewhere I am exclusive. Intention shared means below somewhere I am shared. So if this is intention shared or intention exclusive, I can go and lock this in shared. So I have to be careful to see that I have locked the parent appropriately before locking the child. If I want only to do it in shared, I do this in intention shared. But if maybe I want to do this in shared and this in exclusive, then I will do this IX and this shared and this exclusive. So I will appropriately lock the parent. The fourth point. TI may lock a data node Q in X, SIX or IX if the parent of Q is locked by IX or SIX. This means that if I want to lock a node in X or SIX or IX, then the parent must be locked in IX or SIX. When will I lock a parent? Suppose I want to lock only this node in exclusive mode, I will lock this in IX mode. If I want to lock this in SIX mode, I will lock this in IX mode. If I want to lock this in IX mode, I will lock this in IX mode. But suppose I want to lock this in exclusive mode and this in, say, shared SIX mode. Then I will lock this in XIX mode, not in IX mode. That is, I have to be careful. If I want to only lock this in exclusive mode, then this IX is sufficient. But if I want to lock this in exclusive and this in SIX, then I will lock this in SIX. I will put in an appropriate lock function at the parent which is consistent. If a node A has two children B and C, B in X and C in then IX. The same data item. So this is done by the same transaction Ti. If another transaction wants to lock what? If it wants to lock this in shared, it will first try and lock this in IS. So now is IS and IX compatible? Suppose another transaction Tj, this is by transaction Ti, another transaction Tj wants to lock this in shared. It will have to lock this in IS. Is it allowed? Is IS and IX compatible? Yes. So it will allow it to be locked in. No. No. A lock, this one will be IX and IS. Now what will be the equivalent lock of this? No. Both the locks are available here. This node is locked in IX mode as well as in IS mode by this transaction. This transaction has locked it in IX mode and this transaction is locked it in tries to lock it in IS mode. It is compatible, it will just go through and lock in this in shared mode. There is no problem. There is no problem. This will just lock it in shared mode and go down.
So one node can have two nodes.
One node? No. The point is not like that. There is a precedence between the locks. What is the precedence? See, shared and IX are never go together. Therefore, if somebody is in IS and another one is in IX, which one will you keep? IX is sufficient because IX takes care of everything what IS does. You look at this column and you look at this. Whenever IX is true, IS is true. So, if you have IX and IS, you just leave it as IX and you will see that the compatibility will be through. You just allow it to go through. Is that okay? IX is covered IS. Look at truth. False means what? If IX and IS both exist on a node for a same one, then IX will make it false whenever it is supposed to be false. Okay. And the case where it is not so, like this and this, they are not compatible. They will never occur simultaneously.
Why should we label it IX and not SIX?
Oh, SIX means that this node is also shared and means everything below. There may be a third node here, no? Which is totally free. If I put this as SIX, I will do a shared of the whole thing. And one will be exclusive and the whole thing will be shared below here. And that will be applicable for that transaction. Nobody else will be even allowed to do it in IX mode. Nobody else will be allowed to lock it in IX mode. There is somebody, the third transaction cannot come and lock this in exclusive mode. You will have problem. To two-phase protocol must be followed in the point number 5. The TI can lock Q if it has not unlocked anything. You first lock and then unlock, two-phase protocol. And TI can unlock Q if no child of Q remains locked by TI. That is, since when you, it is the reverse of the locking process. When you lock, you must appropriately lock the parent. Similarly, when you unlock a node, you must unlock all the children below that node by yourself. If you have locked the children below that node in some other odd fashion, then you must unlock it. Suppose you have locked a node in exclusive mode, and you have locked this in intention exclusive mode, and you want to remove this lock. You have to first remove this lock and then remove this lock. Maybe you have locked this in SIX, then you have to remove, and this in X, then you have to remove this and then remove this. Or you may have locked this in IX mode and then lock this in exclusive mode and then this in shared mode. You have to first unlock these two, then you have to unlock this. Otherwise, so if you unlock only this, then somebody else will go in, and you will always get into an inconsistent or deadlocking situation. So if we follow these locking protocols and we avoid deadlocks, then we will have a conflict serializable protocol in which we allow concurrency on the database, and we allow a person to lock either a record or a database or a file individually, and this is one of the most widely used mechanisms of locking. So we have seen several kinds of protocols and in concurrency control, and we have seen the basic issues of what are the types of locking and unlocking mechanisms. So we will stop here.